In this lecture, we're going to talk about iterative methods for solving linear systems. We've already looked at direct methods, and for small systems of equations, direct methods are always going to be faster and more robust than iterative methods. However, for very, very large systems, especially when there is a lot of zeros in the matrix, we call those type of matrix sparse matrices, where the percentage of the zeros in the matrix are very high. An example of this would be like a tri-diagonal matrix. In linear systems that have those kinds of structures, which often in fact arise in the discretization of physical systems of equations, in those cases, iterative methods can be faster than direct methods for solving linear systems. So let's look at what the process of an iterative method entails. So we start with a system of equations, ax equal to b, and we're going to convert that system of equations into the one on the right side. So x equals a matrix T times x plus a coefficient, some constant c, okay? And then what we're going to do is we're going to take an initial guess, x0. A lot of times this is just simply a vector of zeros or a vector of ones, depending on the situation. Or if you know something about where the solution might be, you could have a better guess that would reduce the number of iterations. But ideally, the initial guess shouldn't matter, and we will always eventually get to a converged solution. So we start with an initial guess, and we use this basically just evaluate the matrix product plus the addition of the vector to get a new guess. And then we take that new guess and we plug that back in, and we continue to do this for n iterations. Notice here that I have a superscript 1, 2, and a large n. This is in contrast to the subscript. So when I have a vector x, I've used the notation to for the components of the vector to be x1, x2. So the subscripts refer to components of the vector. The superscript now refers to the number of iterations in an iterative cycle or an iterative method. So we'll continue to do this until some convergence criteria is met. There's a number of convergence criteria you can choose. One of them would be where if x is a vector of, say, the error between iterations, say the error between 2 and 1 or n and n minus 1, we can compute this L infinity norm. The L infinity norm is simply the maximum absolute value of any single component in the vector. We could then compute that, and if it's below some tolerance, we would have the method break out of the iteration cycles. So let's look at an example with numbers. So here we have 4 equations and written them like this. And what we're going to do is we're going to solve each equation for its x component with the same number. So equation 1 we'll solve for x1, equation 2 we'll solve for x2, and so on. And that's what we have here. And I've purposely kind of kept the structure of the equations like this. So if we do that, and then we write this in matrix form, we have this matrix here. This is our T matrix from before. This is what T matrix would look like. Actually, notice for this particular example, the zeros on the diagonal. Then we just stick in an initial guess x0 for the initial guess of x0 equal to zeros. Then this is our x1, and we just continue to do this for a number of iterations until the convergence criteria is met. And so this process that I just outlined with that example is called Jacobi iteration. And you'll notice here in the pseudocode that this is nothing more than a matrix vector dot product where we're ignoring the terms on the diagonals. So in other words, another way to think about that, and the way it's written here is that you wouldn't actually compute those terms, but another way to think about it is if you were to just zero out the terms on the diagonal and then just do a standard matrix dot product from the off diagonal terms, then you would that's what you would get here. Okay, So just some observations. If we take our initial matrix A and we decompose it. Now, this is not the standard, LU multiplicative decomposition. This is the summation of three matrices, right? Where we have the diagonal is just literally the diagonals of A. L is the terms below the diagonals of A, and they've been negated here for good reason, as you'll see as the equations are developed. As well as U is the terms above the diagonal of A, again, having been negated. So that because these terms are negative, when we take D minus L minus U, then it adds back up to A. So if we plug that into our equation, then we can go ahead and do our separation, moving the L and U term to the right-hand side of the equation. Then we have this equation here. And finally, then the solution to that is just the inverse of D. And of course, the inverse of a matrix is just 1 over the diagonal. So that's something that's easy to compute. You don't actually have to do any kind of Gaussian elimination or anything there to compute that. So this would be the matrix form of the Gauss-Seidel iteration. And again, just plugging in then the values for K, right? In this case, the superscripted values again correspond to the iteration. So the value at K would be updated with the value at K minus 1. So, one thing about, if we think about the Gaussian, the Jacobi iteration method, we have this for loop where we're basically looping over the rows of the matrix. So for I is equal to 1, 2, to n, where n is the rows in the matrix, then we're computing x at k, and I'm going to write it in component form, right? So it's xi is equal to the sum over j. Remember in the Jacobi, we say I not equal to j, right? Where j goes from 0 to n, aij xj plus, and I'll just say, in this case, ci. And here we have, this is k minus 1, okay? But for all I greater than 0, all right, so once we've passed the first row of the matrix, then the x at k for that is actually a known value. And so what we'll do is we'll split this summation into two pieces, right? So we're going to not do this anymore because we're going to split it into two pieces. And the first, we're going to go from j equals to 0 to I minus 1. And we're going to compute aij xj, except this time we're going to use the current value because it's already been updated, right? So we're going to use the current value of k plus, for the ones we don't know, I plus 1 to n, aij xj. And then for these, we don't have the current value for k, so we'll just use k minus 1, like before, plus ci. And so this process of using the current value after you've done a few iterations and computed xi of k for the rows above, then we'll use those current values. Otherwise, we'll use the old values plus the constant there on the end. So this process is called Gauss-Seidel elimination. And the pseudocode for that is basically just what I wrote there. Again, we're just splitting the summation from 1 to I minus 1 and I plus 1 to n. And using the new value where we can and the old value where we can't. So this process is called Gauss-Seidel iteration. And we're going to skip the derivation here, but the matrix form of that it looks like this. And I should have mentioned this earlier. There is a necessary and sufficient condition for n minus L. For n minus L to be invertible, for its inverse to exist, then the diagonals cannot equal to 0. This would be the same in the Jacobi case where we needed to compute D inverse. Same condition, the diagonals cannot be 0. So what's not included in the pseudocode is the possibility that you may need to swap rows to ensure, before you start the iteration, to ensure that there are no zeros on the diagonal. So let's quickly talk about the convergence of these methods. And in order to do that, we have to introduce a definition that is the spectral radius. So what the spectral radius is the maximum absolute value of one of the eigenvalues of a matrix. Now, if you don't know what an eigenvalue of a matrix is, we'll cover it later. But for now, we'll just move on. It's a concept from linear algebra. So what we're going to say is that if the spectral radius is less than 1, then there's an identity that says that for a matrix A, I minus A inverse is equal to this thing. Basically, the sum of the powers of the matrix A. So we're just going to hold on to that identity. Again, this is true if the spectral radius is less than 1. The inverse exists, and it's equal to that. So if we then look at our iterative procedure, look at the sequence of vectors computed by our iteration. And what we're going to do is, we're going to start at the end, right? So the vector x to the k is equal to t times x to the k minus 1 plus c. And then we're going to plug in what x to the k minus 1 would be. Well, it would be t to the x k minus 2 plus c. That's equal to t squared, and then you have a t minus I over here. And if you continue to do this, right, then ultimately, for the last iteration, you're going to get t to the k plus this thing over here, which we'll notice looks like what we have up here, right? Therefore, using this identity above, assuming that the spectral radius of t is less than 1, then if the spectral radius of t is less than 1, then we know this converges to I minus t, and that's the inverse over there. And therefore, x to the k will converge to the inverse of I minus t, and we know this will exist if the spectral radius of t is less than 1. Therefore, it is convergent. So the idea here, the point of going over this, there's actually a multitude of ways that you can design algorithms to rearrange your matrix into the form. The idea would be to ensure that the spectral radius of t is less than 1, and then you can ensure that the scheme will be convergent.